Hey Royals, in today's lesson we're going to look at waves and vibrations. These are types of repeated or cyclic motions, and you've probably experienced a bunch of these in your life. If you've ever sat on a beach and watched water waves travel by, then you're noticing waves firsthand. Or if you sat in a living room and they have a grandfather clock and the pendulum swings back and forth, that's another type of wave. These types of motions can be classified into two different groups. The first one being vibrations, and it's repeated motions that have no energy transfer or matter transfer. And some examples of them would be the pendulum on that grandfather clock, or a mass sitting on a vertical spring and it just bounces up and down. The other type of category is our waves, and this is where we're going to spend the majority of our time. And they're disturbances which cause energy to be transferred through vibrations, but we don't have matter being transferred. And so that's important with both of these different types of groups, that matter is not being transferred. So let's quickly take a look at this simulation here that demonstrates how energy is being transferred between particles in our materials. Now, if I were to take one of these particles and I pull it back towards the left on our screen really quickly, you can see that the energy is being transferred from one particle to the next. And so I'll put a little trace on it so you can actually see the energy being transferred across the screen here. So as I pull back, you can see that it was almost like a cascading from one particle to the next. And we'll do it one more time here. Reset. And you can see that the energy that I release is being quickly transferred along these. But the particle itself does not leave the screen, which means that this energy is being transferred from this particle, and I'll just stop them so they stop moving. It's being transferred from this particle to this one, and then to the next one, and then to the next one, and then to the next one, and that the particles stay in place on the screen. They just simply oscillate back and forth, but then the energy is what is being transferred from left to right on our screen here. So some examples of waves would be the water waves that you're seeing on the beach, or electromagnetic waves. So these are your light, X-rays, gamma rays, anything on that electromagnetic spectrum. And the last one of our examples here are sound waves. How you're hearing me right now is a type of wave. Now, to better understand waves and vibrations, we're going to look at a pendulum. And I have one here for us to look at. And this pendulum will demonstrate a bunch of different terms that we're going to use when we're talking about waves. So the first one is the path that this pendulum takes. And in order for it to be repeated or cyclic, this pendulum has to return to its original position. So if I were to pull it back, I'm giving it a displacement away from its equilibrium position. And this displacement is going to be the largest distance away from the equilibrium position that the pendulum can reach. And we give it a special name. We call it the amplitude. And so the amplitude will be the difference between the equilibrium position and the furthest away, or the largest displacement away from the equilibrium position. Now, as the pendulum moves back and forth, it's going to travel 4 amplitudes. So let's trace them. So here we have the first one. There's one amplitude. As it comes down to its equilibrium position, it's traveled 1 full amplitude. And it's going to travel off to the other side, again going through 1 full amplitude. So we're at 2 now. It comes back to its equilibrium position. There's 3 amplitudes, and back to its original position. So we've gone through 4 separate amplitudes. So this is a type of transverse wave. And we know that because the vibration is perpendicular to the length of our apparatus. And so this type of motion is a transverse wave, okay? As my pendulum's getting tangled up on itself. The other type is known as a longitudinal wave. And I'm using a slinky to demonstrate this one. So the slinky also has an amplitude to it. And I'm just gonna change it so that we can actually see the full thing. There we go. And so if I have it at its equilibrium position right here, and I pull it downwards, I give it an amplitude. When I release it, I notice that the energy is being transferred up and down. that's also the length of my apparatus. And so since the energy is being transferred along the length of the apparatus, we call it a longitudinal wave. So we have our two different types of vibrations. We have a longitudinal wave and we have a transverse wave. Now there's another form as well, and it's called a torsional vibration. And I can show it here with my small little optimist. And as I turn her head, you'll notice that her nose will go back and forth. And it's turning versus moving up and down or swinging back and forth. So I'll do it one more time here so you can see that her nose will transfer back and forth and it's twisting. Now that's a type of vibration or wave that we'll look at in a future course. So in this course, we're not going to focus on it too much. So with each of these types of motions, we have a certain amount of time or how many oscillations or how many cycles it goes through in a period of time. So the number of oscillations or number of cycles that the wave undergoes in a certain period of time is what we define as its frequency. And so we have an equation for it. We say that the frequency F is equal to the number of cycles, N, divided by the time that we allow this to happen in. So the units for frequency is measured in hertz or inverse seconds. So that's one thing that has a misconception. Students often think that hertz is a special type of unit. Well, a hertz is just simply 1 divided by a second, or an inverse second, so seconds to the negative 1. Okay, so another way of looking at this type of motion would be to think about, well, how long does it take for it to undergo one full cycle? And that's what we define as its period. So the period of a wave, we say, is the time it takes to undergo all of those cycles. So we use the capital T to indicate period. And so you'll notice if you stare at these two equations here, one for frequency and one for period, you'll notice that they are just inverses of each other. So if we know the frequency, we can take its inverse to find the period, and vice versa. If we want to find the period, we can take the inverse of our frequency. Now, another thing that we want to define when we're talking about waves is the phase. And we'll spend more time talking about phase in our next lesson. But for now, if I had two objects that were both oscillating together, we would say that they are in phase. Now, I'll keep my top finger going back and forth, and I'll try my best to do this. And if I have them going like this, then we say that they are out of phase, because as the top one's moving this way, the bottom one is moving that way. So if they're not moving perfectly together, we say that they are out of phase. Okay, so let's look at a couple examples of these types of definitions. So we're looking at frequencies and periods and phases. So our first example here says find the period of a wave and its frequency if this pendulum undergoes 24 cycles in 1 minute. So let's write down what we know. So the number of cycles is 24, and the time, delta t, is 1 minute, or 60 seconds. Okay, so here we go. Let's start with trying to find its frequency. So the frequency we know is the number of cycles divided by this time. So let's substitute in our values. We say 24 divided by 60 seconds. And we'll find out that if we divide these out, we get 0.4. And remember that inverse seconds, so 1 divided by seconds, is the unit of hertz. So there is our frequency for this pendulum. Now, if I wanted to find its period, I have two different ways that I can do it. Now that I know the frequency, I can say the period is 1 divided by the frequency, or 1 divided by 0.4 hertz. And I find out that its period is 2.5 seconds. That's one way of doing it. Another way to do it, I could say that I want to take the time that I allow this oscillation to occur divided by how many cycles it went through. And if we do that, I get 60 seconds divided by 24. oscillations, and you'll notice that it comes out to 2.5 seconds yet again. So we know that we can find the period and the frequency of a wave based off of if we know how many cycles we've gone through and the period of time that we allow the cycles to occur in. Okay, so the last question here for us to try is we want to determine the vertical distance that a pendulum undergoes if it's allowed to travel for 2 minutes. So we know that the time that we're going to work with is 2 minutes, which is 120 seconds. And the vibration has a frequency of 0.5 hertz. So that means that it undergoes one vibration every which means that every second it undergoes half a vibration. Okay, and it has an amplitude of 32 centimeters or 0.32 meters. Okay, so let's trace this out. Let's figure out what's going on here. So if I have my oscillations, here's my equilibrium position, and I have my pendulum and it's going to oscillate up and downwards. Let's say it goes downwards first, so it undergoes one amplitude. It's going to come back up to its equilibrium position. It's going to travel upwards to another amplitude and then back down to its equilibrium position. So remember in the lesson how we said in one full cycle, the pendulum or the object that is in question that's undergoing this periodic motion will undergo 4 amplitudes. So the length that this pendulum will travel is going to be 4 amplitudes multiplied by how many oscillations or how many cycles this pendulum undergoes. So we want to find the number of cycles. So we can do that by knowing this time that we allow this pendulum to oscillate in and its frequency. So if we remember, frequency is equal to the number of oscillations divided by the time. We can say that the frequency times this time is equal to the number of oscillations. So let's work this through. The frequency is 0.5 hertz. The time is 120 seconds. And that will give me the number of cycles. And this will come out to be 60 cycles. So we now know that in that 2 minutes, this pendulum or the spring will undergo 60 cycles. So let's find out the length of the pendulum, how far it actually moves. So we'll call it delta D instead of the L. So delta D is equal to 4A multiplied by N. So delta D is going to be 4 times its amplitude, 0.32 meters, multiplied by that 60 cycles, and you find out that this pendulum actually moves 76.8 meters. So that's quite far, but if you think about what's actually happening here, is that this pendulum is going to move up and down fairly quickly. Well, this one's not very quick, but it's going to move up and down fairly quickly. So the distance that that bottom of that pendulum moves is about 76 meters. Okay, so this answers the definition of what a wave and a vibration is, and we actually defined period, frequency, and phase as well throughout this lesson. So if you have any questions or concerns about it, please don't hesitate to reach out to me.